And we are back. Okay, so what we figured out so far, draw, red pen, that we know this voltage here by the previous argument is 1.5 volts, and it has to remain 1.5 volts as long as we only have V common mode on there. So we want to find the maximum value of V common mode to keep these in saturation. Well, I know that VD, to keep M1 in saturation, well, this sounds familiar. I need VD1 greater than or equal to VG1 minus VT. So my VG min is going to equal VD1 plus VT. That doesn't sound right. That's VG max. Let me, yeah. Yes, that's VG max. We switch the min and the max, and we'll use the eraser. VG max, to keep it in saturation, will be VD1 plus VT. 1.5 plus 0.4, this is 1.9 volts. So that's the maximum common mode because my VG1 equals V common mode. Okay, now we want to find, that's the maximum, 1.9 volts. Now we slow down and we look at our notes and go to the next slide. We want to find the other side of this. So we've got the maximum V common mode max is 1.9 volts. VCS is what's going to dominate the other end of this. VCS is the minimum voltage across the current source. So this is going to be 0.3 of a volt. That was given to us to keep the current source working properly. So this voltage down here was minus 1.8. The minimum value I can have at the source here is going to be negative 1.8 plus 0.3 is negative 1.5 volts. That's at the source. My VGS is, yeah, I'm getting this right, is 0.6 of a volt. So if I go 0.6 of a volt, no, I'm not. Above there, VS min is negative 1.5, that's right. Oh, okay, never mind. I know what I did. Let's just ignore this for a minute. The minimum value that of VGS I can have to keep this transistor on is VT, is 0.4 of a volt. So I go 0.4 of a volt above that. The very minimum value I can have here is negative 1.1 volt. So I've got to keep my V common mode somewhere between negative 1.1 volt and positive 1.9 volt to keep the transistors in saturation. If the transistors go out of saturation, my circuit goes into saturation and it will hit a positive or a negative power supply rail. Yes.
So we know it has to be negative 1.1 volt because that's
just to barely keep the transistor on, yeah.
Right. So that's just the voltage at that point, 1.5.
Right. Right. So I need at least 0.4 of a volt across VGS to keep the transistor on. The current will have decreased at that point. I will not be in a linear mode of operation. It'll no longer be 100 microamps, 50 microamps, and 50 microamps. And we'll look at some curves later on that will show that what happens as we approach those limits. You don't really even want to get close to these limits. This doesn't mean that the circuit works perfectly at 1.899 volts. the circuit is starting to shut down at that point, and you've lost some of your linearity. I have slides, I have pictures. We'll get to that. If V common mode, equals 0 volts, what is the signal range of VD1? This is for C. Oh, we want to look at the output range. Well, the output range, first of all, let me explain something to you. I diddled on these slides today because there's a point here I thought you guys needed to know. The ID that's specified here is the DC ID. Remember, I can add plus or minus AC signal to that. So at any given point in time, the current may not be 100 microamps. It may be 100 microamps minus 20 microamps or whatever, depending upon how linear it is. So that signal can change. Big ID, the total signal can change based upon the value of the AC signal. The total VGS at any given point in time, the DC, the average value is going to be 0.6, but there's going to be some plus and minus on top of that. Okay, so if this happens, the maximum voltage I can get out of here is when my AC signal is minus 100 microamps, which gives me 0 microamps through that leg, which means I have no current going through there, which puts this at 1.8 volts. So the maximum V out I can have when I have 100 microamps plus some AC signal is 1.8 volts. And that happens at the negative current peak. 1.8 volts equals VD max. Now the minimum value that I can have is going to be determined on when I keep M1 in saturation. So VD min I don't like what I wrote up there. VT min equals VG minus VT. That's the minimum value to keep it in saturation. The minimum value of VG, oh, I know where that came from. The minimum value of boy, I put a lot of thought into that, and I don't understand where. Okay, that's one of my random things. Negative 1.8 volts here. The minimum value I could have here was negative, we're going to scratch this out, we're working on a different problem, is negative 1.5. The minimum value I can have on the gate is negative 1.1. So this would be negative 1.1 minus VT, which is 0.4. And this should come out to be negative 1.5 volts. So my output can range between 1.8 and 1.5 volts. Okay.
So VD min is just equal to VG min minus VT.
VG min minus VT, correct. So this is this, and again, it's not going to work really well at 1.799 volts.
So is that signal range also, can that also be written as the signal swing, or it's the same thing?
This is the common mode voltage. This is how high up and down I can take that common mode range. We'll look at the differential signal swing later. Now, normally, okay, let's think about op amps and how they work, because this will help you guys out later on. If I take an op amp and I put 1/10 of a volt on the positive terminal and 0 volts on the negative terminal, and I leave it open loop, what happens? Yeah, the output rails, because I've got the op amp itself has this huge gain, like 100,000, a million, something like that. 1/10 of a volt times 100,000 is higher than the two signal rails. It's going to rail at one of the power supplies. That's the way you operate an op amp as a comparator, is I put a voltage difference on the inputs. If I put, the way we keep these things stable and still have a differential signal on the input is we put a feedback resistor, or we put some kind of feedback loop between the negative input and the output. And that cuts the gain of the circuit down to a point where it's like 5, where I can actually use it as an amplifier. So small differences in the differential inputs are going to cause the output to either go, one output to go high and the other to go low, or vice versa, depending upon which way it is. We are not putting feedback into these differential amplifiers. I did it when I've done it once with Jack Gerard. In the 380 lab, is actually put a feedback resistor in there and made it work. For purposes of this class, we're running them all open loop. This is what happens, and this was like the next slide too. Good point, good place to do that. If I take this VN differential and I make it a really small value, it's small enough so that this isn't going to saturate, like 50 millivolts. I put in a VN differential. What's going to happen? I have a, let's say 0.5 volts. So I have 25 millivolts here, and I have negative 25 millivolts here, and this isn't a very good op amp. I put the signal like that. Is what's going to happen is this voltage is slightly higher than this voltage. They have the same VS. So M1 has a higher VGS than M2. Let's write this like this. VGS of M1 is greater than VGS of M2, which means philosophically, when I look at the saturation current equation, if VGS is higher, then ID of M1 also has to be greater than ID of M2. As soon as I put a differential voltage across this thing, the current no longer splits evenly. And Cedar-Smith goes through about 2 pages of stuff where they derive this, and they say, okay, this is going to be ID1 when I have a differential voltage, and this is going to be ID2. And you get that equation, and that's derived in the textbook. Now, I went through here for these examples, and I actually did the calculation and plugged them in, and I found that in case A, ID1 was 62.3, 1, 2, ID1, ID2. It doesn't split exactly the same anymore. ID1 and ID2 is 62.3, and this becomes 37.3, and those are in microamps. If I look at case B, I put, they go the other way. It becomes 37.3 and 62.3. If I increase this, case C, where's case C? It is basically going to be 73 and 26.6. If I go to case D, I put 2 volts across there, and I'm frozen. 87.5 and 12.5 microamps. If I go much bigger than putting 0.2 of a volt difference across there, all the current's going to be on one side, none of the current's going to be on the other. One of the transistor goes out of saturation, which puts my total circuit into saturation, and it's going to hit the power supply rails. I will be back. I'm sorry, I got excited.